Alright, Chapter 4, Step Function, Response for the Adjustment of the Controller. In order you live with the data product for the characterizer of the name of the method described by the previous chapter, the necessary for the analyze with the control action that may be combined with each property. Most commonly used with the control action with a two position action with a single speed floating action, proportional speed floating action, proportional position action, proportional plus reset action, proportional plus reset plus rate action. In order to obtain with a step of the function with the response for the permanent control with the necessary for the disconnect with the with the final control element. In this case, with the electronic control with the ammeter is connected and with the specified load resistance of the car for the control output with the hydraulic control with the sense control controllers. A cylinder piston with an negligible in the air friction replay the final controller element with the piston motion is picked up with a differential transform with the pedometer similar device with a converted signal suitable for recording pneumatic control with the controller output with the signal with the applied with the pressure record with the medium pressure drive with the primary element must be kept with the constant condition during the test. Step input with the producer sudden small with the adjustment with the controller pointing setting mechanism figure 4.3 compared with the arrangement with the step function set for the process with which for the control of the figure 4.1 closed loop show the connection normal operating condition figure 4.1b over the loop it is open with between the step input with the step function record with the final control element profit of measuring means. These mean with the test does not investigate with the by process with itself with the combination with the final control element the measuring means. Figure 4.1c the element of the control is inserted between the step input with the step function record with the two tests together with the compromise over the components of the loop. If the measuring means of the final control element, or if combined with the controller instead with the process of the pure approach, and show the reference of the input with the set point going into the say I don't know pump or controller to the final control element to the process measuring means, and that's in a closed loop. So go with controller final control element process that means controller final control element process means. Alright, this you have a separate controller, and then the step input goes from final control process measuring means step function recorder. And then from 4.1 you have the step function test, which is the step function process response from the controller, step input controller, step function recorder, and then final controller element are in their own side of the loop with the process, and then and the means of the measuring is loaded back to the input controller. Typical controller action could not be obtained with a particular region of the arrangement shown. Discussing step function response with the various controller actions, two successful input steps shown in figure 4.2 will consider the time one with the first step to apply with the initial output, the second step with the time two with the second step with the increase the input above the initial input, 12 with the magnitude first step chain with the exemption or the two position single speed floating control with the which for the step of the input with inherently some absolute magnitude. Step input with the controller says. Two position action, process without dead time with the illustrate with the liquid level of the control system, solenoid valve control with the flow in the tank. Controls include the two metal rods of the M and N, which portion part of the which form the part of the electric. So here we have a controller going grounded into change 1, change 2, back to the controller, one above the flow level, one below. Final control element with a valve on it, and then the flow rate out of the tank when that's grounded, also liquid level control. So basically you have a valve going into constant 1, which is a tube, and then when it reaches constant 1 tube, the level goes up, turns the control, and then adjusts the final control element. Circuit closed through the ground connections indicate with the liquid itself with the tank wall with the electric conduct with the condition of the shown with the level will arrive at the reach of the metal rod. But at that point with the electrical relay energized locked and shutting down with the solenoid valve remains closed until the level drops far enough for the open and the circuit of the three with the metal rod. With the unlock with the relay and of the relay is energized. Locked to maintain with the valve open and with the level rises again to M. The other rod. The only one two input rod signals possible, either calling flow or not to call for flow. The output with the tank level is similarly limited to the two alternative positions. The process eliminated illustrated figure 4.3 show the self-regulation since flow out of the tank and the creep of the height of the level due with the head pressure for the same with the rate of the liquid flowing with the speed with the response with it becomes smaller with the level that rises. Process response with the hence with the comparable to figure 3.3c with the last process with the start point with the empty tank with the solenoid valve with the fully open level rises above along with the process curve of the A illustrated figure 4.4 on reach from the C1 change 1 solenoid valve closed to the level that will now begin with a drop along with the inverse process with the response with the curve B on 4 force over the process with the two-position control system without dead time, and that was on reaching level C2 with the valve open with again with the difference between change 1 and change 2, the corresponding with the difference length between the electrodes M&M figure 4-3 with the call of the differential gap of the control of the smaller, differential gap of the control of the short if the period of time and the greater of the number of the times over the minute opening with the close of the cylinder over the frequency of the operation, how large frequency with the largely question over the life of the expected with the solenoid valve with contained context associated equipment, the frequency given number due with the given and profit of widening the differential gap of this become means that over the level of the tank will be oscillated between the wider limits with another factor for the determinative of the period with the two time is the process respond to the process for the large time comes with the slowly respond to the process for the longer period, i.e. Slower the process for the smaller the differential gap of the hinge for the closure for the limits for the process for the control of the same frequency solenoid valve operation. Since the response curve of the A and B with the correct with the change with the level of the fully open and closed with the correct with the can be duct with the to do with the response which would be below the limiting the valve stroke with the two extreme with the positions a quarter open and three quarters open. Reduce the stroke with the 1/2 or full stroke with the constantly reduce the flow with the variation caused by the controlling action from the high low and bypass adjustment usually available to the solenoid valve for the purpose of also saying any limits between the valve with the operating thus make possible the operator with a closer differential gap without changing the frequency of the operation limitation with the method given by magnitude of the load chain with the maximum consumption of liquid for the tank. For the example, should not exceed the low capacity of the maximum opening with the minimum consumption should not be less than the flow of the capacity minimum valve open. The period of the time depends on set point with the control of the example, the controlling the levels with change 1, change 2 with the result. Long period between level of change 1 and change 2 with the general longest period with the obtained with the controlling controlling toward either the upper and lower level of the tank. Profit dead time. Process for the dead time. The conclusion of the two-position control system with the dead time must be modified with the dead time of the present has been shown in the previous chapter for the concept of the dead time. Also applied with the process consistent with several capacities with the connected with the bioresistance, such as a process illustrated in figure 4 or 5. This is a two-position temperature controller. Show the bath, the heater element with the electrical power, and then the two-position controller and the electrical power going into the bath. If the temperature control with the temperature control with the electrical contact with the thermostat with the brake with the temperature for the reach with the determined the predetermined point with the temperature drop with the more with the differential gap of the contacts. Again, with these contact with the open clove with the electrical shift with the energy of the heat element, thereby with the regulator with the heating of the process with the electrical current with the increase with the temperature of the heater element with the relative of the first capacity with the heat with the flow with the resistance of the material with the heat even embedded with the consistent constituting another capacity with the bath itself with the enclosure for the further capacity of the resistance to be considered with all the result of the process with the dead time and the response with the special schematicized in the graph of the figure 4-6 as shown with the process that had been shown with the cold condition and contact with the temperature control with the short circuit. The temperature would rise along with the dash line up of the level determined by the self-regulation system thermostatic cuts of the heating system at controls change to with the temperature of the will still continually rise, some of it to do with the dead time with the delay of effect. And time constant sufficiently long with it much more and more gradually slope of the response with the curve figure 4-6 show the core overshoot with the corresponding process respond with two-position control service position with the dead time. Correspondingly with the rejuvenated and hence with the relative length of the dead time and the ratio of the time dead time over time 1 respond with the overshoot with the two-position control with approximately y. Overshoot is y over the gain over the dead time over the 2 times the time of 1. Dead time 2 and 1 with the dead time constant respectively g with the process for the game with the control of the switch with the one position over the other heat tree. Heating furnace on off control may have with the process for the game the 2400 degrees which may be the room temperature for the 100 degree with the furnace temperature will increase with the 2500 when fully heat with the supply of self-regulation increase the heat level the limits of the possible temperature increase the point with the process for the game the sense for the 2400 degrees. Assuming the furnace have the dead time of 0.8 minutes for the time of the constant for the 16 minutes for the overshoot with the 2400 degrees Fahrenheit over the time minutes over the divided by 32, which was the 2 times the time 1, which was 16 minutes. So you have 32 minutes, 2400 degrees Fahrenheit over 0.8 minutes times 32 minutes equals 60 degrees Fahrenheit. In furnace for this control level 14 degrees Fahrenheit with the breaker thermometer will probably show with the temperature oscillate between 1340 degrees with 1460 degrees Fahrenheit with the heat treated with the material with the however become with a relatively large capacity that may maintain comparatively constant temperature even under wide fluctuation. Furnace temperature for the above the formula does not consider the contribution of the differential gap of the overshoot of the amplitude of the Y, which was shit, what was it? Is 60 degree with a quite obvious for the differential gap of the neglect for the wear with the magnitude of the wire comparatively small with a different gap of the neglect of the amplitude with the dependent with the differential gap. There are several methods of the overshoot with the amplitude wherever the differential gap contributing essentially to overshoot with the most of the obvious steps to reduce the differential gap. This is how the mechanism is limited for the backlash loss of motion and by a metallic thermostat, for example, it's hardly possible to reduce the differential gap below with 1.5 degrees Fahrenheit. Another method is accelerator of the heat element frequently built when the thermostat with the energized round with the later call for the heat of the primary element usually consisted by metallic reps from the additional heat of the accelerator that therefore cuts off the heat source before the upper limit of the differential gap that actually reach the equivalent reduce the differential gap hence the limit overshoot. A third methods were frequently used the heat treating furnace with the consistently operating with the slower heat produced with the rate with the heats of the lung with the time come with approaching the set point with the heater rate and use the chart with the void delay with the lower relay rate with reduce the overshoot with the multi-position contract switch multi-position controller switch automatically change with the one rate with another price set with the temperature load change in figure 4.7 show the effect of the load change by the means of the 3 curve of the normally load curve of the curve that has shows the load final control element with a set point with a control variable, the control point of time 1, 2, 3, 4, and 5, and 6, and off set and control point. Position with the final control element with the curve of the fluctuate for the control valve with the control variable. The control variable assume with the temperature for the valve with the response with the consider be included with the dead time final control element for the example of the valve with the steam heating system and shut down with the control variable to reach for the temperature. Control change 2 with the temperature 1. However, to do with the head time with some of the overshoot with the temperature with the begin with the drop to reach change 1 before the valve opens. Change controller 1 opens again with some of the overshoot with the difference between change 2 with the change 1 with the differential gap of the time to 3. Time 3 with the valve with the clove with the O again with the butt shutter after the load charge chain with the constant consider with the more heat input with the valve with the clove with the temperature drop with the faster with the rate than before. This is equivalent to the shorter time with the constant result with the larger for the time 2 over the time 1 ratio, hence the larger the overshoot with expressed with the graph. Temperature finally builds up with the, again with the slow rate with the center of the load continue to be large for the consequence of the overshoot with the time 5 and 6 is small. Nevertheless, the amplitude of the oscillation has increased considerably. Another effect of the shift of the time of the ground control variable oscillates the separate of the control point from the set point with the term of the differential with the gap consider with the set point with the initial side with the center of the oscillation low with the chain with the shown figure 4.7 and the center of the oscillations have the drop and indicate with the central indicated by the control point. Original set point with this control point are identical to the are after load chain with the separated with the offset. Conclusion: the following conclusion could be made with the two position action. The control variable to oscillate with a certain amplitude over the above and the below of the set point with 2 with the given process the low with the amplitude depends on the differential gap of the minimum 3 the minimum differential gap that generally limited mechanical conditions 4 and profit without dead time when the minimum differential gap is also limited maximum permissible frequency with the operational limit of the final control element of the frequency increases inversely. Time comes to the process with the end of the process with the short time and the constant with the not with the two position action and a process with the dead time overshoot with the limiting factor with the differential gap of the low with the overshoot with the dependent with the ratio for the dead time with the time constant dead time over the time constant on the gain G. Hence the process for the large of the dead time over the time 1 ratio large of the gain are not sustained with the two position control of the number 6 the number of remedies available to improve the response with the two position control of the high level high low and bypass spread adjustments and with the solenoid valves accelerators multi-position controllers. 7 the difficulty cover the overshooting and improve the load chain with despite with the limitation of the greater number of the profit of the industry with the two position action with the result of the most simple generally most economic control with a single speed floating action. Figure 4H with the single speed floating action, floating control with the variable with the liquid level ahead with applied with the pressure below. Alright, show the single speed floating action controller, show the floating motor on the bottom and up at the top of the liquid level ahead. And then I show the cam, a crank, capacitor, a spring-loaded valve with its adjust and power supply. Increase level of the pressure for the ends for the expend for the bellows for the result of the contact between A and B, A, B, and C, A, B, and C. Okay. Which of the contacts, A, B, and C, are contacts. C is inversely the degree for the level of the A and C with a certain amount of the level chain of the make over the mid position C without making contact either side of the range pressure chain with the neutral zone. Motor shaped pool reversible single phase. The motor is a shaded pool reversible single phase motor. If the winding D energy with the crank with the cam and the rotate with the counterclockwise. If E with the energized clockwise, they travel limited with the 180 degree with the means for the O for the cam and the mount with the motor shaft with the actuate limited with the finger switches F and G for the example the contact C code for the on A the winding D energy for the motor rate rotates counterclockwise until it's open with a contact with the F D energy of the winding D. No further action occurs within contact with the closed C and B instead of the motor clockwise rotate for the crank rotating with the motor shaft would be linked to the final control element. Process without self with the regulations above the control position of the valve with the water line with the boiler drum. If the boiler drum is equal to the cross-sectional area of the real with the height with the value with the suddenly open with the beyond with the requirements for the process level the right with the contingency, the character of the defined with the process without self with the regulation, let the shift initially band with the condition as shown on the figure 4-9 with the key for the control without the neutral zone before. Show the load supply with the control variable level the process without self-regulation flowing control no neutral zone, and it shows time 1, 2, 3, 4, and 5. Time 1 given the load correspond with a certain value with the opening with the sure with the even the with the supply with the maintain with the control variable. The level of the points up the line with the time 1 the load chain with the ends of the chain with the depends with the increase of the level of the drop of the figure 4-8 can be seen with the result of the chain with the contact C moved on A energy of the motor with the open to the value with the increase of the supply shown figure 4-9 which valve with the line S correspond with the supply flow with the tank with the dash line with the M represents the rate of the liquid removed from the steam the valve opens with the supply with S equals the demand M the rate of liquid removed, which for the curve of the time, the dead time or time interval 2. However, this is pointed out enough supply with the demand as long with the deviation set point of the per system and add supply with the requirement to make up with the deficient liquid level of the valve, therefore with the continuity open with the time interval 3 with the time control variable to recur with the set point. With this point with the valve with the 2 wide open in which because of the system supply with the returnal level the set point with no longer need the valve become with the close with the time 4 with the half with the level to continue with the rise since with only have the valve obtained opening M and which if the delivered required with the quantity have with the time and the level of the 2 have with the ends of the valve get reducing the flow with the required level to reduce the time interval 5. The time interval 5 however the situation same with the time and the interval 1 namely the supply with a non-efficient for the load demand with the cycle starts again. Assuming the dead time is added with these conditions, the response given for the worst, the dead time will make if the process well with the control of the following example, the control will assume the call for the dead time will be covered the motor of the consist cause slightly before it reverses the type of the touch coasting is illustrated in figure 410. At time interval 1 load increase the control variable begins to drop. Shows the load supply and control variable set point. Process without self-regulation, floating controller, actuating motor coasting. Action for the control of the gradually with the increase of the supply. S for the N reach for the M line with the time interval 2. Which time control variable to begin with the return of the set point with the reach for the time interval 3. At this point with the motor shift with the D with the coasting continue with the movement of the time interval 4. The M line with the dot cross with the time interval 5. The increase of the amplitude respond with the control variable to the available or already visible with the time interval 6 to 7. The motor coasted with again with the 4 reverses then resolve with the further amplitude with the increment with the observer the control with the rapidly with the maximum amplitude with limited mechanical condition continuity oscillate within the amplitude limit to set with the control of the undesirable single speed floating action, thereby not be within process without self-regulation, process with its self-regulation. Alright, the above the description situation chain with complete with the process game with the self-regulation, typical example of the air conditioning systems above the motor, X-ray figure 4A with the position of the damper, the ducts, with the admitting with the high with the recirculating drum of the dryer temperature with the control variable below. Bell and within the bellow of the figure 4-8, maybe to consider the gas fill with the shield on the drop temperature for the gas contract for the bellow of the move it moves with the contact C with the move toward A with the controller where disconnected with the temperature for the manually change toward the closure for the temperature would drop with the drop of the now not continuity indefinitely as in profit without self-regulation but with level of the new temperature for this is because of the degree of the dryer temperature for the heat loss of the roof of the ducts and wall of the dryer that becomes less. Figure 4-11 illustrates for the action of such system with a dead time is neglected with a dead time warning. The suddenly increase the heat demand offsets ensure the load supply with the control variable temperature set point with the M and S and the time interval 1, 2, and 3. Process self-regulation floating contactor. Bend with the temperature start with the drop with the lead with the gradual opening with the dampener with the warm air supply with the previous example of the S line with the example of the portion of the flow of the control element simultaneously with the flow of the control system. The M line interprets the flow leaving the system and waits for the present with the case of the heat loss of the dryer system. This flow leaving the system no longer counts with the figure 4, 9, 4, 10, but become with a function of the control variable. When the temperature drops, heat loss diminishes with the express with the M line with the reflect with the oscillation response with the control variable, the control with the S line with the M line indicate with the point with the supply equal to the heat loss with the heat. This have with the temperature for the 2, with the moment with the temperature begin with the temperature for the 3, with the edge the 7 with the point with the reach with the dam with the begin with the clove with the fact with the M line with no longer straight with the deflect with the direction shorten time until M equals S with the head and the dam with the effect with the dynamic action leads with the rapidly subsiding cycle. Control system is stable to prove the process with the self-regulating lens itself with the controller floating action figure 4.1 also will illustrate with the fact with the greatly speed of the damper motor with the zoom with the M line with the reach with the small with the will be amplitude temperature oscillation with the true with the ideal with the system. But at dead time of the time constant must again with the be taken into account with the practical application of the magnitude of the dead time produced with the overshoot with the response with the quite similar to those illustrated in figure 4.10. Differently with the damper to respond with the figure 4.11 the resulting oscillation not necessarily increase the amplitude of the rapidly subside. Offset prescribed previously described with the two position control of the kinetics if the floating control of the lower with a floating controller along with the deviation of the control variable exhibit the larger with the neutral zone with floating controller produces corrective action. Floating action controller provides gradual corrective action when the faster of the profit of the response of the control of the time of the constant of the speed of floating speed over the controller left the necessary will be removed with the final control element in order to obtain with the necessary change over the control variable. Hence less than with the amplitude of the overshoot for the same reason the time constant of the measuring element should be small with compared with the floating speed with the contract over the controller implied with rather serious limitation of the floating speed with the hence speed correction and load changes occur as long as these load changes and proceed slow and a slow and correctively action with a reminder of the importance of these changes that are fast and the time has elapsed before the control variable to return the set point and they become objectionably long. Conclusion. The following conclusion might be made with the single speed floating action. Single speed floating action can be used but only with the process with the self-regulation. Smaller with the dead time of the time constant with the better for the control. 3 floating speed with hand speed with the corrective action has to be slow. Relative to the time constant with the process with the measuring mean with the keep the amplitude with the oscillation with the acceptable limits. 4 relatively slow corrective action permissible at the time of the control action become the most obvious with the hence objectionable with the process with the first load changes. Proportional speed floating action. With this action from the speed with a proportional deviation of the control variable to set point with the action 7 over the controller can be half and far over the spread and single speed with the floating controller be covered in reducing deviation of the control variable to bring in the back 0 automatically slow with the down the floating speed. Even the most frequent with the hydraulic control with the hence for those applications are not only advantage with the proportional speed floating action but also with the higher power output with the hydraulic actuator if it's desirable with the large team with the higher butterfly valves. It's such a figure 4.12 with the illustrate with the action of the proportional speed floating with the control of the process pressure for the control variable to apply with the diaphragm with the deflection with the diaphragm depends on the magnitude of the process of the pressure of the spring constant over the spring with opposing the force exerted with the process of the pressure of the spool with the 4-way valve connecting with the diaphragm level through a leveler system results in spool position proportion with the process pressure for the spool control of the oil flow with the actuating signature cylinder with the position shown in the precipitous zone with the control variable to set point with the process of the pressure with the rises. Spool move it downward with the connect with the lower port over the cylinder oil supply the upper part of the drain. As a consequence, the actuating piston move it upward inversely with the degree of the process of the pressure result with the downward motion of the actuating piston. Alright, so you have the diaphragm and the process pressure piston. Process pressure from the diaphragm going from oil supply 4-way valve, which has the oil supply and drain 4-way valve actuating cylinder piston. The actuating cylinder and the actuating piston. Personal speed flow floating action. The piston is linked with the final control element, which is the position according to the speed of the actuating piston. Depending on the rate of flow of the oil of the groove of the four-way valve, of the rate of the flow of the function valve opening, since the opening of the four-way valve, the creep of the DBA for the control variable of the set point, valve of the actuation position with the move fast for the lever, DBA for the two character with the proportional speed floating action for the illustrative of the motion of the final control element of the control. Use along with the deviation control variable, the set point per se at the end of the speed of the final control element, move with the proportional to the deviation control variable from the set point they are over the course limitation, but both variation speed of the motion of the final control elements for the motion on the discontinuity end of the stroke of the reach of the speed and cannot be faster than the oil supply allows. Alright, I'm calling X for displacement final control element of the T for the time required with the displacement. I'm calling X for displacement final control of the time required with the displacement. The ratio X to over T expresses the floating speed with the proportional deviation E with the control of the variable set point. So you have the ratio floating speed, the ratio expressed as floating speed, and or equals deviation times F. F is the constant called the floating rate, which is floating in the deviation controlled at the set point compared with the response single speed's proportional speed. Floating X illustration for later for the gradual deviate, I believe it is deviation. Degree of the floating speed with the control variable approach with the set of the point with compared with the abrupt changes in the single speed system. Alright, so here we have the single speed floating contactor neutral zone deviation floating speed set point. Proportional speed floating contactor set point floating rate floating speed and floating band and deviation. The speed xt with the final control element expressed by n and hence so the final control element is equal to the floating rate of the controller over e with the deviation control variable set point. Floating speed is n limited to the maximum speed over the obtainment of the control of the free with the conservation, but the object of the floating rate should be high as possible without sustained oscillation. Adjustment of the control allowed with the attainment of the optimum flow rate. Adjustment of the flow rate with the a slow floating rate with identical with the low sensitivity of the controller, vice versa. Figure 414 shows the servo that respond with the control variable, assuming the initial rate of time is the initial rate at t is equal to 0 the set point chart with the change 1 to change 2 to the slow floating rate. Low sensitivity will result with the overdamped response with the edge shown the flow rate with the increase of the maximum point at point which will no overshoot with the change 2 with the this is called critical damping expressed with the corresponding curve of the figure 414. For further increase of floating rate result of the oscillation, the quarter decay ratio in between the each with excess of the overshoot of the quarter over the magnitude of the previous one. For the similar over the decay ratio reduce the overshoot with the 1/2 previous one. In the interest of fast corrective action, limited to overshoot with a quarter could decay with a ratio generally preferred for the single capacity process. For example, the quarter decay would allow for the operation more than 20 times faster for the under the critical damp conditions. So figure 414 shows the various degrees of damping. Controller can change 1, 2, and 3. Have over damped critical damps, and then you have half and quarter inch delay at half decay ratio, quarter decay ratio on change 2. Floating rate of 1/4 decay ratio over the process with the dead time is given in its floating rate of final control element in minutes, inches and minutes on unit chain with the control variable is equal to 5 over the divided by the gain process of the gain on units control variable in inch of the displacement over the final control element in times time in a constant in minutes. Dead time 2 with the presence of the multiple capacity process with the broken down in single time constant plus with the dead time allowance has to be made correspondingly actual practical methods efficient accuracy most application based on the equation. K is the number chosen in the following table. So it equals the floating rate of the control element in minutes per minute even chain with the control variable is equal to the number chosen following on the following table times gain divided by gain times T1 plus T2. Alright, so we have the greater rate time at 225, 12 to 25, 6 to 12, 2, 6, 1, 2 is smaller than 1. For example, the temperature control of the process gain of the 5 degrees and 5 degrees Fahrenheit an inch of the valve motion, dead time 1 inch minute, Time comes at 3 minutes. Substitute with the value of the above the equation floating range, and then you have the floating range is equal to 2 over the 5 times 3 plus 1, or 0.1 inches minute Fahrenheit. Method of determination: floating rate actually installed with the system. Consider the following steps. Increase floating speed with the critical setting of the control set of the beginning of the oscillator with the change of the amplitude, measure the time needed for the per unit length of the stroke with the final control element under these conditions. Estimating the relation from the time come for the dead time with the time 1 over the time 2 with the edge of the degree for the floating rate. So the time is measured for the second step with increased by the factor listed in the following table. 25 to 100, 10 minutes, 10 times, 10 to 25, 5 times, 4 to 5, 10, 3 times, smaller than 4, 2 times. Step will give no values beyond time 1 over time 2 equal to 100, since beyond this value it is generally not possible to obtain continuous oscillation. Limitation: critical settings. Rules for a critical setting of the given of the different mechanism of the character in this chapter require with a certain qualification. Respond with the product of the load chain, with depend on the nature of the load chain, with where the load chain different origins. Respect with it all should be investigated. Feed water heater on a feed water heater, for example, the temperature may be the influence amount of the throughout the put the steam by a steam pressure. Hence, critical settings should be repeated with the keep the setting point the answer for the chain with the steam pressure for the slightly. Setting should be determined whether the method requires with less sensitivity. Further, non-limited areas may exist, etc. With the chain with the position over the final control element, the chain with the magnitude of the control variable, the variable characters you to make of them relation to the end, least approximately linear with the non-linear or too high with the control system may be stable to valve position, unstable to do another answer for the chain with the variable value character for the reduce the sensitivity of the control sufficiently accommodated with a wide enough range of the valve openings. Proportional position action. In proportional speed floating contrary described above, the position fine control element is independent of the deviation of the control variable to the set point of this for the deviation persistent the final control element continue to move as far as the mechanical limitations allow. Proportional position controller on the other hand, the response will become the function of the deviation from the control variable. Figure 4.15 shows the response with a different control of the similarity between the two positions with the name of the proportional position with the control of the insofar with the response is an immediate in the other one in the other case if it does not correctly graduate floating controller. The corrective action called for the proportional position control to modify the fine control element spring up over the diaphragm should not respond with immediately certain time required the move of the one position to another. Figure 4.16 compare the proportional position action of the control with the last with that control of the final control element combined with the show of the final control element become the limiting factor in the vast corrective action. Proportional position control of the proportional position action is used equally in electric, electronic, or hydraulic pneumatic controllers. Figure 4.17 illustrates the pneumatic action of a single over the control the variable to apply with the by as a pressure to signal bell over the increase of the pressure for the tend to rotate with the flapper over the flapper clockwise with the bring the flapper close with the nozzle through the J's in the opening which air flows out supplied with air process as with the fixed restriction and through the nozzle of the atmosphere of the movable flappers over the nozzle tip with the come with the variable restriction the airflow passes through the two successive step input the two position action. Proportional speed floating action, single speed floating action, proportional position action, and we have that step 4.15 show the response various controllers, and then we have respond with a proportional position controller with or without final control element, and it shows A responds with the control alone, B can respond with the control and final control element. Alright, now we move on to another drawing which is the proportional position controller pneumatic action. We have a single control variable with a single bellow with a nozzle with a flapper, the feedback bellows, diaphragm, fixed restricts, nozzle, supply port, pilot valve, atmosphere, diaphragm, exhaust port, and two final control element. Pressure drops one fixed restriction or the variable to restrict the pressure between the two restricted nozzle back with the pressure assume the variable. You determine the flapper position. Flapper approves the nozzle for the nozzle back with the pressure for the increase of the which move the way in and it decreases. So the relation between the flapper and the position of the nozzle back pressure for the linear only with the relatively small pressure change with the center of the further the flow capacity can be handled over the arrangement, rather limited with the customary use of the pilot valve with the increase of the effect with the flapper nozzle arrangement with the regulate the airflow to the final control element, the nozzle back pressure applied with the diaphragm with the pilot valve with the connect with the diaphragm with the plug with the three-way valve with the which with the connect with the final control element through a supply port to the supply air with which are exhaust with the ports for the atmosphere with the supply port with the end of the cause exhaust port to open and vice versa. Again, they are restricted to connect with the with the supply port with the exhaust port. Both restriction variable and perfectly exist between them and is applied with the final control element supply. The single over the control variable to rotate with the flap of the clock while the nozzle back with the pressure increase for the exhaust port closed. Supply port open the hinge with the pressure between the two ports increases the increase the pressure and transmitted not only the final control element but also the feedback bell with which now exerts with the counterclockwise forward with the flap of the picture with the fourth balance between signals below the feedback bell over the feedback bell over the balance of the position terminal deflection from the flap of the hinge of the signal transmitted the final control element. If the final control element is spring up over the diaphragm value, with the usually spring the pressure is converted with the force balance within the force of the spring, roll the finite position final control of the element with a proportional single frame with a control variable to step function response, proportional position controller illustrated in figure 415 expressed by x. The change of the controller output is equal to 100 times p with a proportion 100 divided by p with a proportional band percent times E, the magnitude and step up input with the meaning of the proportional band is discussed in detail further below. Offset. Most important limitation proportional position control with the inability to return the control variable to the set point with the load chain with the curve of the deviation. This is illustrated in figure 418 with the regulations applied with the indicator of the central curve of the corresponding with the output control of the final control element combined. Chain with the control variable expressed with the low curve with the representative of the input with the control with the proportional position control with the output with the inversely proportional to the input of these curves that must be correspondingly with each other, the one beginning with a mirror image of the other after the load change. Control variable to begin with the decrease of the supply, arrive at the purpose of the increase of the supply with the bring the control variable back to the set point. However, impossible for the proportional position controller because of the base of the control variable to supply maintain with the proportional of the mechanism to do with it not permit with the maintenance of one set point over the other operate with the higher level of the proportional position control can only reduce the deviation of the control variable of the set point but cannot eliminate it remaining. The deviation is called the alpha that is shown in figure 418. The extent to which proportional position control of the reduce the deviation would occur with the curve of the deviation reduced in factor Q. For example, the feed water heater is rated with the feed water temperature of 180 degrees for a given steam of emission. And show the loads to supply and control variable the proportional position action and the offset. Load with this temperature maintained as long as a certain average of the feed water demand with the boiler exists. However, the peak period of the temperature will drop 106 degrees. You with the automatic control, you with the let's control variable with the output of temperature feed water, and the control agent with the being be the steam is above the control system and the prevent the feed water temperature from dropping below 178 degrees. This means without the control of the feed water temperature for the good be decreased with a minimum of 20 degrees Fahrenheit. With the control of maximum, the decrease is reduced to 2 degrees Fahrenheit, allowed with the deviation reduction factor of Q is equal to 180 degrees minus 168 over 180 minus 170 equal to 20 over 10 of 10. The obvious higher quality less for the permissible effect. Deviation record reduction factor of the product of the consideration proportional position control with determination approximately a half the decay ratio of the known into the time constant dead time and mean with the equation Q is equal to time over the time plus 0.8 over the time 1. T2 plus 0.8 times time 1 over time 2. The time constant above the feed water heat in 3 minutes for the end of the dead time of the 0.5 is then 0.5 plus 0.8 times 3 divided by 5. Whichever the desired quality of the control of the 10 would now be obtained with the feed water temperature may drop to 176.55 degrees Fahrenheit and would correspond with a deviation increase with the fact that the particular profit is another way to improve the quality. Desired quality control is to increase the amplitude of the oscillation method to ignored since they generally is not acceptable. If the drop is not permissible, the proportional position control that cannot be used with the deviation reduction factor, therefore means to determine the proportional position control of the acceptable specific control system. Or your adjustment proportional bandwidth. The proportional bandwidth is trained with the control variable is necessary to remove the final control element. To do the full stroke that usually is there is here with expressed in N% of the total measuring range of the control instrument, with the instrument with the total range of the 0 to 200 degrees Fahrenheit may have a 10% proportional bandwidth. This means with the final control element move the full open to fully closed with a temperature change of 20 degrees Fahrenheit. Proportional band may be expressed with the unit of the control variables with the corresponding with the full movement of the final control element. For example, proportional band at 10 degrees Fahrenheit the means with the final control element move through with a full stroke with a temperature control variable to chain with 10 degrees Fahrenheit. For smaller temperature chain with a movement over the corresponding smaller with a narrow with a proportional band with a faster response. Smaller offset with a greater tendency to oscillate. Figure 4 and 19 show the controlling action various proportional bands and shows a typical response with the process of the proportional controller. P is the chemical solution considered with the control variable with the sum of the chain with the alkalinity with the curve with the time one with the proportion band with the equal to 20% of the control variable. The return of the variable that quickly set with the point continue the oscillator around with the sympathies. Assume subside with the gradually with the acceptable particularly with the mixing tank with the equalization solution, assuming have the oscillation considered with excessive with the proportional band 50% maybe the child with the response level with the overshoot with the reduce with the considerable to be offset with the consequent. Further increase with the other proportional band to 10% of the result with the even larger offset with the overshooting, eliminated with the completely adjustment for quarter decay ratio with the presuming the lie between 20 and 30% of the proportional band with the control with the quarter decay ratio could be determined with the experiment with the calculation based with certain numbers of the habit and know the methods of the calculation should be discussed further, either by one of the following questions. The proportion is equal to 100 times the proportion of the band percent of the measuring range of the equal to the control range of the equal to 100 times the response rate in units control of the variable of minutes of an inch for the motion final control element times the dead time times s stroke of the inch of the control element move of the control output and signal changes through the full range, and r over the mean of the range controlling instrument of the unit of the control variable, and then and then it's also the proportional band is equal to 100 times the gain time over the time, dead time over time, interval 1, times the stroke in inches over the means of the range control instrument over the units, and then, yeah. Alright, the magnitude of the time count with the dead time of the do not refer to the process along with the result of the step of the response with which include the final control element and profit of the measuring element, for example, the maximum response with the phase process for the value with the display for the 1 inch for the 20 degree Fahrenheit with the dead time with the 10 minutes for thus stroke of the 2 inch of the measure range with the control instrument with the 200 degree Fahrenheit result with the proportional band. For example, the method is assumed with the control P in proportional bands equal to 100 times 20 times 10 with the 2 divided by times 2 divided by 200%. Experimental method is assumed with the control system and the operation limited amount of the profit distributed on permissible the first step of the time with the critical statement of the proportional band adjustment between with the variety due to the proportional bands to the point where it continue with the oscillation constantly with the amplitude beginning to appear with the most speed on the successive step of the average chain with the proportional band with the low chain with the introduce small chain with over the step of the point respond with the observe with and respond with the still with the stable over the proportional band with the maybe defer with the reduce with a single step constitute only with the adjusting proportional band with its wife with the critical stability is corrected with the adjustment with the quarter decay ratio. For example, the critical setting with the continuous oscillation bringing into a period proportional band with 10% of the suitable proportional band for a process with the 20 portable proportional band of 20%. Alright, proportional position and versus proportional speed floating action. Factor limited to the application floating action floating rate with the stability with the control system may require a very slow flow rating, and in this case of the correction deviation may be to cover the slow of the time which elapsed before the control variable to return with the control of the point with the longer than permissible satisfactory control, and you have your slow flow rating compared with the wide portion broad with the proportional position control. In either case, speed curvature action is limited to interest of stability from the equation. The follows you have the low time 1 over time 2 ratio with the high over the time 2 over time 1 ratio. The diminished response with the speed proportional position action. Equation found proportional speed and floating control is equal to K over gain times 1 times 2. So with the time 1 over time 2 ratio effects of the floating control action extend with the constant K. Table page 42 show the maximum effect with the K does not affect with the ratio of 5 to 1. Magnitude sum of the time 1 plus time 2, however, there's much more pronounced effect with floating control of the would have with the proportional plus action, propositional action. For conclusion, proportional position control of the particular value with a large value with the dead time with the time constant with the concern with the ratio of the time 1 to time 2 with is also a large proportional speed with floating control of the verse of 2 is true profit with a small value with the dead time with the time constant small ratio with the time 1 over the time 2 rates with the best suited For example, the temperature control prop for the time count for the range for the dead time warning for the suitable proportional position control for the disregard offset with the alpha of their hand. pH control system mentioning alpha they have the time counts for the 0.02 minute for the dead time and 0.48 minutes. Proportional speed floating control would be probably the best answer. Proportional plus reset action. Figure 420 illustrates proportional plus reset action pneumatic arrangement with the same as in 417 used. You have a flapper single bell, a reset bell with a readjustment rate with a feedback and mechanism shown with the proportional plus reset feedback to final control element. Example of pilot valve over the ignore with the sake of a simpler parameterization. The reset bell is added to support the initial pressure of the bell for the reset of the feedback with the bells is equal to the pressure signal bell of the correspond. Set point pray for the torque exert of the three bells for the flapper balance the other signal increase for the flapper and move with the clockwise 10 to close the nozzle. This result in increase for the nozzle back pressure for the bitch is applied with the feedback bell itself. The result of the position of the flapper and the nozzle back pressure is then thus determined the new balance of force exerted with the bells. However, increase the nozzle back pressure for the grad for the leak shear with the restricted knee valve with the designated with the illustration reset with the rate adjustment and doing with the reset bell with the continue to move the flapper for the clockwise direction when the beginning of the action with a single bell with the out nozzle back pressure continue to arrive with the effort with the increase the control output signal with the at the point with the control variable to final number return with the set point proportional plus reset action combination proportional action and proportional speed floating action. This result elimination of offset from the proportional offset position action. Reset integration action. Figure 420 show the compare with the step function respond with the reaction proportional speed floating proportional positioning proportional plus reset. It shows proportional speed floating action and then proportional position action proportional plus reset action. That's time over W. There are two steps to the input that I have implied with the actuating signal with the time 1 and time 2 with the retrievable second with the input twice with the large of the output distraction of the first one with this action proportional speed floating control with the expressed as W where change of the controller output signal is equal to the frequency of the floating rate times the actual signal actuating signal times time with the interval measured in time 1 time 2 with the respective means for the long as it gets for the actuating signal. Controller output signal which continue the increase degree for the actuating signal E, which is the actuating signal is multiplied by the time of the continuing action function time of this integrating action. Offset cannot exist. The integration action actuating signal was also the result of the offset with the offset with the deviation of the control variable to set point of the actuation signal. The difference between the control variable to set point if the proportional position controller is shown in figure 421. Actions expressed as W. Change the controller output signal equals 100 times the proportional band times E, the actual signal. The proportional band of the controller, in this case the actuating signal E, produced the change of the controller output signal of the finite magnitude change is not large enough. The result of the offset, which result of the proportional position control does not provide an integrated action. Equation corresponding with the proportional plus the reset equals output signal equals 100 times proportional times the actual signal 100 times proportional times actual times whatever factor of the reset rate with the controller times time equals 100 times the proportional times E times the proportional reset rate of the times I times T. First term contained with the proportional position control with the second term with the corresponding with the floating control with the floating rate with the is now played with the 100 times the factor reset rate with the controller time proportional band with it multiplied with the elapsed time due to the integration of the action control eliminates offset. Step function response with the proportional plus reset with the action illustrated in figure 421 show clearly the distinction between initial sharp and increase with the proportional action and the integration action of the reset with the proportional plus reset controller may be considered with the two speed with the proportional speed with the floating control with the first of the fast with the chain with the flow by the more gradual change. This becomes a particular opposite for the additional action final control element considered this valve with the gradually vertical chain with the controller output signal. The chain of the action due to the proportional control to the reset action is only chain with the speed with the response with the final control element. The reset rate with which was the factor reset rate with the controller above the equation depends on the open needle valve with the reset with the rate with the adjustment figure 420 with the depends on the pressure with the differential curve and hence magnitude chain with the control output signal with the figure 422 with the illustrate with the reset with the rate with the K for the initial corrective action control with the response with the key with the deviation. Shows incremental with the controller over the output in inches and PSI. 1.2, 2.4, 3.6, 4.6, and 8 in minutes, time in the minutes. 0.2550, 0.57 in time intervals. Control variable, incremental transmitted pressure at 1.2 psi with a which for the do the proportional position action only. Corrective action, increase the reality effect with the reset with the action 4.8 psi. A minute with the hinge with the reset with the is equal to the 4.4 repeat minute as opposed to the control that has usually an output of 3 to 15 psi, which is the signal range of the final control element. Corrective action of the time is 0 due to the proportional position action only. It is 1.2 psi or 10% of the output range. 15 minus 3 would equal 12 psi. Hence the W would be equal to 10% of the time interval 0. The proportional band would be 50% of the then at time interval 0, and the actual signal is equal to 100 over the proportional band time the output signal actual signal 5%, which means the response illustrated would call the deviation control variable to set point 5% of the instrument with the signal. The reset factor was stated at 4 repeats within a minute. It followed after 1 minute. So we have the output signal of 100 over 50 times 5 times 1 plus 4 equals 50%, which expresses the PSI controller output change of the 6 PSI figure, which corresponds to figure 422. Adjustment proportional band reset rate with adjustment with the proportional plus of the reset control of the game with the made E with the experiment with the calculation give the measuring range of R over the control of the stroke S for the final control element with noting of further either process response rate with the dead time or the process game of time constant with the dead time adjustment can be made with the following expression: proportional band equal to 100 times the V times I forget what V was. Variable times dead time times stroke over range. You have proportion 100 times gain times dead time over time 1 times stroke times the stroke over range. This equation is the same as those used before. The proportional position control of the reset range is 0.3 over the dead time. Example, to give the proportional position control over the dead time of 10 minutes. Adding reset of the controller would require the reset rate of 0.3 repeats a minute. The experimental method files steps outline proportional position that determine the critical situation and setting with a proportional band with a continuous oscillation beginning to appear. Reset actions cut out with the time minute for the time between the two successive maximum of the oscillation. Critical setting is measured with a suitable final adjustment. Proportional band with the same with the proportional action of alone with twice the critical setting. The reset rate is 1.2 over the time total time. Proportional plus reset plus rate action. Alright, proportional plan with the contractor controller could be only reduced to determine the point with the point of the controller system become the unstable speed with the correction of the wire band, the less of the resistance of the hinge of the slower the correction. The lagging correction becomes particularly noticeable aware of the time concept of the measuring element is noticeable magnitude. Typical example of the multiple capacity of the temperature control of the system. In this case, the equivalent of the time relatively large become the multiple capacity of the wide range, wide proportional band with addition of the measuring lag with the primary element of the considerable result of the relatively slow correction for a deviation control variable from the set point. It is desirable to such case for the creative of the response slow chain of the actuating signal by accelerating the signal over the control of the give the fast response with which one would slow down the control of the variable returns to the set point, preventing except for the overshooting the hinge of the instability of the control of the provided with the rate of action. The result desired response with the occasionally proportional action for the provided with the rate of the action only whenever the rather than rare. More frequently, the controller in case conclude that all reset action become with the proportional plus with the reset place rate. Control of the region of the proportional controller can operate with a normal proportional band that does not generally require the reset action, since the offset of the insignificant. In this case, however, the narrow band provided with a quick effect with the quick enough for the corrective response with the rate of the action hardly warranted within the command becomes wider in response and slow with the offset with the larger reset for the action become the necessary for the action rate of action in certain conditions. Figure 423 schematic illustrates for the proportional plus for the reset plus the rate action and the difference for the figure 420 with the fourth bellows. The rate of bellows is add to the area with the feedback bellows with the smaller with the chain with the signal with the deflection from the flap of the more larger due to the reduced area of the feedback bellows with the now controller output signal transmit with the final controller is assumed. So now we have the signal bellows, rate bellows, rate adjustment, adjustment. Feedback bellows, reset bellow. You have a reset bellow, signal bellow, reset bellow, feedback bellow, and rate bellow. We have the supply air going to the final control element. To be proportional flapper direction, chain with the control output signal to gradually transmit the rate below with the root with the restriction of the rate, time and adjustment, reduce the initial deflection of the flapper. If the pressure over the control variable is applied with the signal bellow with the chain with the slope with the pressure for the control output signal the chain with the slope with there will be no large difference between the pressure for the feedback with the rate bellows. However, the fast for the control variable chain with the larger the below with the pressure difference with the greater the effect with the rate of action. The response of the proportional plus the rate of the control of the input will be maximum only limited to mechanical condition system. Hence, inherent characteristics could not be fully represented with the step function response chain with the control variable, therefore be represented by a RAM function input signal the more gradually chain with the magnitude illustrated in figure 424 at time interval 1 and U beginning with the degree of the controller input signal and output signal reside corresponding with the rates of the dead time to or input signal stop with dead time signal stops create the remain with the concept of the new level fit with the rate of action subside with immediately with the point with determined with the proportional bandwidth however the action with the reset of the mechanism alter with the continue the increase of the controller output signal through slower rate with the time 3 and 4 input signal to increase the time faster with the magnitude chain with is larger than the action corresponding reflect with the controller output signal rate time with the mathematical expression proportional plus rate action equals output signal is equal to 100 times the proportional band time with the actual signal plus the 100 times proportional band times signal goes factor rate factor times time plus 100 times proportional times SE which is the input signal time is expressed times D with the constant expressed adjust rate with the controller equal to 100 times over the proportional band equal to actual signal equal to the factor of the factor times T times the signal is expressed and the input rate of change times D the constant expressed adjusted rate with the controller. Last term stand with the rate of action, the rate of change with the input with the signal expressed is by SE. For example, the input signal to give it in the moment with the chain with the 3 psi a minute, then the SE is 3. Constant D with the adjusted rate with over the control of the rate of the time given with the minutes and to give it the time difference in response between proportional plus rate with control of the, for example, assuming the controller has no reset action factor of 0. One hand, the output signal would be 100 times proportional times the actual signal times the signal expressed and in change in input times the constant expressed with adjustable rate of the controller. The control variable to change with a certain rate and then after the time a control variable equals the actual signal is time with the change with a certain rate times T after the time the control variable. Equation could be written as output signal equal to 100 times proportional band times control variable changing change certain rate at times T A the time after times the controllable changing rate times D expressed adjusted rate of the time controller. Suppose the rate of the action when the habit has been cut off would have been taken longer time to express the time over the same signal magnitude the same magnitude W controller output with a 100 W equals 100 over P times SE times T. Equation 2, 3 both express the same magnitude 100 times P with the SE with the T SE with the D equals 100 over P over the times SE times T and this reduces down to D is equal to TB minus TA, which show the rate of the express the difference between the time due for the proportional action only and the time that it takes for the combination proportional plus the rate to obtain the same control of the output. For example, if the proportional band is 25% of the measurement range of the control of the controller variable change at 50% of the minimum minute is SE50 with the proportional action only with the controller after 1 minute is W with over 100 over 50 times 50 100% of the range. Additional rated action with a rate time of 0.25 minutes for the same chain with the obtained 1 minus 0.25 or 0.75 a minute. This could be changed with an inserting value with the increase of the 2, which give it 100 over 50 times 0.75 plus 0.25 times 50 equal to 100%. Alright, your adjustment of proportional band and reset rate and time equations can be used to determine the adjustment rates for the proportional time. Proportional band is equal to 80 over the Variable dead time times stroke time over the range, or 80 proportional band 80 over the gain over the dead time over the dead one. Time one initial time times stroke over the range. Reset rate is equal to the reset rate factor of 0.5 over the dead time. For the rate time is equal to 0.5 over the dead time. Use the same example of proportional position action proportional band. Proportional band is 80 times 20 times 10 times divided by times 2 divided by 200 or 160%. Reset rate is 0.5 over 10, 0.05 repeats in a minute. The rate time is 0.5 times 10 to the 5 minutes. The experimental method to proceed with the step of the outline proportional plus reset. Control of the adjustment of this valve of the proportional band should be in 1.7 times critical setting. Reset rate should be reset rate 2 over the time of the 2 successful maximum oscillation critical setting. The rate of time should be equal to D over D equals T times 8. Chapter 5, Frequency Response.